Yes, applying the math vocabulary to checking critical points. For this function, I took a relatively simple function I'll mention in a moment where you need to be careful. R2 is mapped to R. With this function, we first determine the gradient of the function. That's the first term. Determine the gradient and write it here as a column vector. Partial differentiation, in this case with respect to x, the partial derivative with respect to x would be minus 2x. With respect to y would be minus 4y to the power of 3. It doesn't matter what is written here, you just need to be able to do partial differentiation. First, we specify the Hessian matrix. Yes, xy is what it's supposed to be. First differentiated with respect to x, then differentiated again with respect to x. Yes, that means we can understand the second partial derivatives. We have minus 2 times minus 2. Not minus 2. First with respect to x, then with respect to y is 0. First with respect to y, then with respect to x is 0. And first with respect to y, then with respect to y, that's minus 12e squared. Well, if you have a problem with partial differentiation, you should take another look at some practice exercises on that. Then the critical points, we set the gradient equal to 0 minus 2x minus 4i cubed. And this leads us to minus 2x equals 0 and minus 4y cubed equals 0. As I said, it's relatively simple here, and here the next term here is, of course, solving equations depending on whatever function may be there. Here it's relatively simple now. We have the critical point 0, 0, which we now check in the Hessian matrix. So HF at 0, 0 is minus 2, 0, 0, 0. I've made a video about this as well, explaining how to proceed and which criterion you can use. If you compute the eigenvalues here using the determinant, you'll quickly see that one eigenvalue is equal to 0. And that means this matrix is semi-definite, so we can't perform an eigenvalue calculation at this point. That's all we can say, which means we have to proceed further here. And if we now substitute 0 into the original function, then we get 0 as the result, yes. And at the same time, it holds that f of xy is less than or equal to 0. For all x and y in R squared, yes, no matter what you substitute, both will be positive. Minus minus will definitely result in a negative number. That means we don't just have a local maximum here, but even a global maximum. Here we've now applied all the vocabulary, and with the corresponding exercises, I hope that at some point you'll say, math vocabulary recognized, danger averted, and you'll get through easily.